Now, I have given you, I've saw some examples here. And I believe you can take your time to go through those examples later. But before we do that, recall that I talked about, compounding interest discretely. What about when you compound them continuously? That is, you would like to know the interest that you have to pay at any point in time. So here, some sort of dynamic, process, comes in at any point in time. You may want to know, what your interest should be. You recall the formula that I gave you that we discussed earlier. That is this formula, the last formula that we have over here. When we take that formula, as you can see over here, we can reorganize it. Okay, it is very to reorganize this formula as you see in the third sort of equation, and notice what we have inside. What we have inside is equal to the value E. Okay, so if we substitute E for that, recall that when I gave you the formula for E, you can go back to the slides and look at the definition of E. So when we slot that inside, we get the value we have over here. So A being equal to P e raised to the power RT. What it means that in a situation where compoundings are made continuously, you are going to use this formula. Now, let's look at this simple example. And we have P being, 250, our R being 15. We have been told to, compound interest for 3 years, yearly, quarterly, continuously, right? So in all the first situations, I here, you use the formula P into bracket 1 plus R raised to the power T. The second one, the quarterly. Then you introduce the formula we discussed earlier. And then the continuous one, the last one, you use the continuous formula that we have over here. The details of the solution is what I have presented here. I have some simple examples for you here, and I would like you to take your time and look at them, and if anything at all, we can discuss at the chat room. The solutions to that one has been presented here. You go through here, the solutions continues. Notice that good thing is that you have to know how to work with, simple exponential and logarithm functions. So the earlier mathematics that we discussed is very important. If you don't know how to go, around discussing or working with simple algebra of exponential functions and logarithm functions, some of these manipulations may be difficult for you. So my little advice is that you go and understand the mathematics, the algebra behind the exponential and logarithm functions, and then the applications are going to be very easy for you. Right, there is also one example here which you can take your time. The question is there, the solution has been provided, and I have some activities for you here. Please take your time and go through all. This activity is quite interesting, and it will help you understand the topic better. Sometimes we also talk about, nominal versus effective rates of interest. And when you express anything in nominal terms, you are expressing it as it is today. As you may know, nominal income, real income, right? But sometimes we always want to know the effective rate. That is the actual rate that is trying to remove the impact of inflation and other sort of impacts on these nominal rates. And therefore, we try to talk about effective rate. And in order to find this effective rate, we need to equate the two equations that we have over here, and then we manipulate it, and we are able to get our effective, effective rate. I think further, there is also a situation here when you have discrete, and I've provided some examples, and the examples are what? So you have the nominal rate, how do you calculate the effective rate? Or you can have an effective rate, how do you calculate the nominal rate? And these are examples that I've given you here, both in situations when you are compounding discretely or when you are compounding continuously. Another application, so now we've come to the end of our discussion of applying exponential functions and logarithm functions in sort of interest compounding. The other one that I would like us to discuss is when we are discounting. Okay, discounting simple means that we are finding the present value of a future value. Okay, we are finding the present value, okay, the value of something today, something that will occur in future. Now, if you look at the formula that we gave for the discrete compounding when m equals 1, or where one compounding is made every year, we had a to be equal to p into bracket 1 plus r raised to the power t. What this implies is that the a, okay, or the PV, or in that formula, that is what I said, it was P. That is a value that you are collecting today. So the P, I have just denoted it by what? PV over here, present value. Now the A, which you have to pay in future, that is when you collected the money from the bank, is what I've denoted by FV, which is future value. So the formula that we discussed, I can put in the form that the future value is equal to a present value multiplied by 1 plus r raised to the power of t. So the question here is that how do you find the future value when you know, how do you now find the present value when you know the future value? Simple. In this equation, all what we need to do is that we have to find the PV, right? That is the present value, and that will just mean dividing the FV, that is the future value, by 1 plus r raised to the power squared. And that is what you see over there. Okay, so when I do that manipulations, I get the formula you have over here. And again, you could see that we're discussing for a situation where we have one compounding a year. But again, when you have n compounding in a year, then our formula can, reduce to the one you see over there. Okay, the one, or when you have multiple compoundings, then we have what you see over there. Similarly, if compoundings are made continuously, then our formula changes over here. So what I can say is that discounting maybe is a reverse of what compounding, right? Discounting is just the reverse of compounding. And again, I think it should be a little more easier for you to find, we have 5 values over there, as in the other case of compounding. So when any 4 of them are given, you should be able to find the 5th one. Depending on how the question is framed, you should be able to extract the relevant information that has been provided and look at the one which has not been provided and for which you are being asked to calculate or to find. Here, there are simple examples that I've provided, in a case when interest is compounded semi-annually, in a case when it's being compounded continuously. And you can see me first trying to put the formula down, inserting the relevant values, and trying to come out with the figure that is required. Coming out with a figure that is required. Now, the last application which I would like to discuss with you, it's how we may be able to estimate, growth points from data points, right? Or how we may be able to estimate growth rates from data points. For example, it may happen that the population of students in the University of Ghana, let me be a little simple, in the year 2000 was 100, okay? And then, coming down to 2007, we may know that the population, has skyrocketed to, let's say, 1,000. Now, if we estimate that the growth rate is exponential in nature, then we will be able to estimate the growth rate. The good thing is that once we are able to assume that the growth rate is exponential, first of all, and once we know 2 data points, we can make projections of what the student population will be in the next 10 years. So what happens is that the first point is when you have 2 data points and we make an estimation that the growth rate of a certain population or whatever economic variable is, we are able to know the growth rates. One is growing exponentially, and once we know that, we are able to make forecasts or make estimations of what the population will be in future. I'm going to demonstrate this with a very simple example, as you can see over here. And in this example, I'm saying that if you look at a certain country, the population for 1990 is, as you can see over there, the population there, it's 500 billion, and then this population went up to 1,250 sort of billion in the next 10 years, that is in 2000, right? Our problem now is to estimate, the growth rate if we assume that it's continuous or exponential, and also if we assume that it is discrete, right? It is discrete. And how do you go about this question? First of all, we will look at the situation when it is continuous. Notice that the formula that I've put over there, the GDP in the year T is equal to the GDP in the base year, which I represent by GPO 0, subscript 0, and then e raised to the power RT. So I take my period, initial period 1990 as 0, and then I will take the year 2000 as 10, because the difference between 1990 and 2000 is 10. Now, the good thing is that if I allow my initial period T to be equal to 0, it makes calculations easier. Okay, it makes calculations easier. So with the help of these, I'm able to formulate these two equations. Okay, I'm able to formulate these two equations. And once we have two equations and two unknowns, all things being equal, we assume that, even though the equations are not linear, in this very case, we know that we are going to get unique solutions. So here, you have to show your prowess in the exponential and log functions. So find the two variables that are there, and you now have to use your strength in exponential functions, and then to do that. From the first equation, I'm always able to know that GDP 0 is 500. I slot it in the second equation, and then I use my knowledge in exponential and log functions to solve for R, which you can see over there. Now, once we know that R, it means that we are able to put it back into that equation, right? We are able to put that into the equation, and then we have the expression for the exponential growth of, the population that we're talking about. We can now, talk about the equation. The equation is not very clear over here. I hope it's going to be a little clearer in your slides. But once we have these equations, we are always able to do our estimations. Now, the second point is that we're looking at a situation where, it is discrete. Okay, the growth rate is discrete. So instead of using here, we use the discrete sort of formula, as we see over here. Two equations, two unknowns, non-linear, but I know with this very equation, you are going to have unique solutions. And the unique solutions, the first one, the GPO 0 is 500. We slot it into the second equation, and then we solve that, and we have our R. Once we have the R, we put it in our equation, and the last equation you see over there is the growth rate of the exponential functions. So once we have these values, now we can do any forecast. Okay, whether we assume that the growth rate is continuous or discrete, we are always able to forecast, what the growth or what the population will be in the year 2020 or 2100 with the help of the assumptions that we have made. Further, I've provided some activities, and I would like you to take your time and see how you can go through those activities. And I'm quite convinced that once you've gone through these 4 activities, you will be able to understand the topic very well.